Right, so Assalamu alaikum. So I'm going to write down the Schrodinger equation again. So this is the complete form of the Schrodinger equation when the particle is moving with slow speeds. This is the non-relativistic form of the Schrodinger equation. Please be quiet. So now we would like to start solving this equation today. It's a differential equation, as we all know. And solving this equation, as I mentioned in the earlier class, means that we would have to find out this wave function as a function of position and time. So we suppose that the wave function psi, which is a function of position and time, can be factored out as a function of position and a function of time separately. Okay? For example, if I have a function like this, e x squared into y, can I write this function as e x squared into e y? I cannot do this. However, if I have a function like this, e x squared plus y, I can write this as e x squared into ey. So this is a function, I have factored it out into a part that only depends upon x and a part that only depends upon y. Alright? So likewise, if I have a wave function capital psi, which is a function of x and time, I would like to factor this out, separate out the spatial part from the time part. Okay? So this is my guess. So I am thinking of finding out a wave function in which the position part can be separated out from the time part. Such a guess is also called an ansatz. Now this is a capital psi, whereas this is a small psi. Okay? So the small psi depends only upon x and f depends only upon time. And the complete wave function is a product of the spatial part with the time part. Okay? Now I have this ansatz or this guess and I put it into the differential equation. I obtain the following: minus h bar square over 2m d square dx squared psi, a function of x, multiplied by f, function of time, plus vx psi x ft equals iota h bar d by dt psi x f of t. Okay? Now what happens is I'm taking the double derivative of this product with respect to x only. So this appears as a constant. Any function that does not have any x variable in it appears as a constant. Okay? So the left hand side becomes minus h bar square over 2m. Now f of t is a constant. I can take this out of the brackets, I can bring it before the derivative, and I can write d square psi x dx squared plus Vx psi x ft equals. Now this product, the product of spatial part and the time part, what is appearing as a constant here? Psi of x is appearing as a constant here. So this can be brought out of the derivative, and I obtain iota h bar psi x, the derivative with respect to time of ft. So this is what I obtain. Now I divide both sides. By psi x ft. Okay, so what do I get? Okay, are you with me on this? So if you look at the left hand side, does it have any time term in it? And the right hand side, does it have any space term in it? No. So the left hand side is exclusively an x term. The right hand side is exclusively a time term. And both x are varying and time are varying. So this term should vary with x and this term should vary with time. But both of them are equal. If this is a spatial part and it's equal to a temporal part or a time part, then what should each of these be equal to? Should this depend upon x? We know it doesn't depend upon time, but should this depend upon x? It should not really depend upon x at all, because if x is kept constant and time changes, then this thing changes. But this appears to be constant because x is held constant, but that's not possible. So if this is a purely spatial part, this is a purely temporal part, and both of these constants, both of these expressions are equal, then each one of them has to be equal to some constant. You see, the left hand side only depends upon x. So if you vary t, if you vary time, does this left hand side change? No, it should not change, because it does not depend upon time. It only depends upon x. But this right hand side, does it change by varying t?
Yes.
Yes, it does. It supposedly does change with varying time. But this left hand side does not change. The right hand side changes. But then you cannot preserve this equality. You cannot have an equality. So even though this term appears to have a time part in it and this term appears to have an x part in it, both of these terms are always equal. Hence, both of these terms must be equal to a constant. ठीक है? इसी तरह अगर हम we vary x, if we vary x, the left hand side changes, but the right hand side should not change, because this does not depend upon x, it only depends upon time. But if this term changes and this term does not change, then how will you preserve the equality? You cannot preserve the equality. So if you want to preserve this equality, then this term must be a constant, this term must be a constant, and both of these terms must be the same constant, because there is an equal sign. Okay? So let's call this constant E. Later we will show that this E is equal to an energy. Do you agree with me on this? Or no? अब बताओ, समझ नहीं आई बिल्कुल? बिल्कुल समझ नहीं आई. If I write down this equation, 3x equals 40. Okay. Now if I keep t fixed, and I vary x, what happens to the left hand side by varying x? You vary x, the left hand side changes, right? But what happens to the right hand side? It does not change because it does not have any x in it. So what's happening is that the left hand side is varying, whereas the right hand side does not change. This is the right hand side. But is the left hand side now equal to the right hand side? No, it's not. Therefore, if you want the left hand side to be equal to the right hand side, if you want to respect this equality sign, then this cannot depend upon x and this cannot depend upon time, which means that both of these terms must be equal to some constant a. It's very simple. So now you have a left hand side which is totally spatial and a right hand side that is totally temporal, which means just depends upon time. And both of them are equal, so they must be equal to, each one of them must be equal to a constant, and we call that constant E. Okay? I don't think it's a very difficult concept, but I see blank faces. Why do I see blank faces? You don't understand this? Differential equation solve करते हैं जब आप, तो this is your first guess, and if it gives you the correct answer, if you find out a function which can be factored out into space and time and you put it into the original equation, if the original equation is satisfied, then your guess is correct. Here, if each one of these sides is a constant, then your guess is correct, which means that this is indeed a solution. So now if we look at what we've done so far and we just look at the left hand side, minus h bar square over 2m 1 over psi x d square psi x dx squared plus vx psi x plus vx equals the energy, equals E. Okay? The left hand side equals E. So now I multiply both sides by psi x. I obtain minus h bar square 2m d square psi x dx squared plus vx psi x equals E psi x. So this is another form of the Schrodinger equation which only has the space part in it. Okay? There is no time part in it. It just has the space part in it. This is called the time independent Schrodinger equation. Okay? So what is V? What's V? It's the potential energy. So if there is a V times the wave function, the dimensions of this object should be the same as the dimensions of this constant. So this is also an energy term. This represents the total energy of the particle E. This Vx represents the potential energy of the particle, and this therefore must somehow represent the kinetic energy of the particle. So the total energy of the particle is the sum of the potential energy and the kinetic energy. This must somehow represent the kinetic energy of the particle, and is a wave function associated with the particle. Now let's try solving this equation for a simple case. Okay? Do you understand the chain of thoughts that we followed? We wrote down the full Schrodinger equation. We chose a guess for the solution, and we put that guess in. We found out that the left hand side only depends upon space, the right hand side only depends upon time, and both of them are equal. So none of them should depend upon x or time. Both of them should be equal to the same constant energy. And then I picked up the left hand side, equated it with energy, and I obtained this equation. This is called the time independent Schrodinger equation. Now I'm going to solve this Schrodinger equation for one of the finest examples, which is very illustrative and will tell us a great deal about quantum mechanics and the behavior of the particle or the wave function. And that problem is called potential in a well. Or potential well or particle in a well. Now you have to be very attentive. Suppose we have a particle, say an electron, that is confined to a one-dimensional well. एक कुआं है और उसके अंदर एक मेंढक है, और मेंढक कुएं से बाहर नहीं निकल सकता. Likewise, you have an electron or a photon or any particle that you can think of, and it is doomed to remain inside a well. It can never go outside. Alright? So this is a picture of a well. This axis is the x-axis, so it's a one-dimensional well. This center point is x equals 0. Alright, let's call the left wall x equals 0. This is x equals 0, and the right wall is at L, is at length L. So the length of the well is L. An electron is confined to this well. It cannot go outside. Suppose you have a DNA molecule, and a DNA molecule is a long chain. It's a polymer of nucleotides, and you put an electron onto this DNA molecule. Now this electron can only remain on this strand, on this polymeric strand. It cannot go out. So this electron is confined to a one-dimensional well. It cannot jump off this strand. It is confined to move in one dimensions. Likewise, an electron is now confined to move in one dimensions, and it cannot go outside the well. Why cannot it go outside the well? It cannot go outside the well because if I have a mountain and two mountains, and there is a valley in between the mountains, and there is a small animal, for example a rabbit is trapped inside this valley. Now these mountains have a certain height h. So if this rabbit would like to come out of the valley, the rabbit would have to climb the mountain. It would have to gain a potential energy equal to mgh, so that it can go to the summit of the mountain and fall on the other side. That is, it needs to escape the valley. It needs a certain amount of energy, and that energy this rabbit needs, E, is greater than mgh. Okay, so if this rabbit eats up a large amount of grass and its metabolic rate is very fast, so that it keeps on building chemical energy and it keeps on mustering enough energy that this energy it musters is greater than the potential energy, it can escape this valley. Okay, this means that this rabbit has a certain amount of energy, E, and it is confined inside a region with walls that have a certain height, and that height represents the potential energy. Okay, so if this energy is greater than the potential energy, the rabbit can go out. Likewise, if in this case the electron can never go out of this region, which means that these walls represent a barrier of potential energy. Okay, the height of these walls represents the potential energy. Okay, now if this electron can never go out of the well, it's destined or doomed to exist in the well for all times to come, then what should be the height of these walls? What should be infinity? These walls should have infinite height, which means that the potential energy goes to infinity at the left wall and the potential energy goes to infinity at the right wall. And in all of this region, the potential energy is infinite. In all of this region, the potential energy is infinite. And inside the well, we assume that the potential energy is zero. So now what we have drawn in this region, V equals 0. In this region, V equals infinity. In this region, V equals infinity. So we define three regions, 1, 2 and 3. Okay, here the potential energy is infinite. To the right of the right wall, the potential energy is infinite. Now what we would like to do is we would like to find out the wave function of an electron. There's a particle that you call the electron, and the common folk call this particle an electron, and this electron is destined to remain inside the well. We would like to find out what the wave function of this particle is given this kind of potential energy distribution. Okay, that the potential energy is infinity here, and 0 in this well. So what we're trying to do, we're trying to solve the Schrodinger equation. We must identify what the potential energy landscape looks like. We have to identify the potential energy. We know the mass of the electron. What we would like to do now is, suppose we know the energy of the electron. Okay, this is known, and this is the unknown. Psi x is the unknown. So we would like to see how the wave function varies in space. Now a very simple question. What is the wave function to the left of the left wall? आप बताओ आखिरी रो में wave function क्या होगा for negative x values? तो आप बताइए. इस रो में से कोई मुझे बता दे. वेव फंक्शन इंफिनिटी कभी नहीं जा सकता. एनर्जी, व्हाट इज द वेव फंक्शन? मुस्तफा, आपका नाम मुस्तफा है ना? क्या नाम है आपका? सी। आप बताओ। 0। आप मुस्तफा है ना? हाँ जी। नहीं हाँ, 0 क्यों है?
क्योंकि पोटेंशियल एनर्जी इनफिनिट होनी पड़ेगी उसको वन probability.
There is no probability of finding the electron in region 1, and the modulus squared of the wave function tells you the probability. So the electron cannot exist in region 1, so the wave function here has to be 0. The wave function in this region is 0. It has to be 0 because the electron cannot have infinite energy and it cannot overcome this barrier. It can never go outside the barrier, so there is no chance of finding the electron there, no matter how long you wait and how many experiments you perform. And what's the wave function here? Okay. So in this region we found out what the wave function is just by logical argument. Here the wave function is 0. What we have to find out is the wave function in region 2. It cannot be 1. So we have to find out how this wave function changes with position inside this region. And inside this region, what is the potential energy? 0. So I write down the Schrodinger equation inside this region, minus h bar squared 2m d square psi dx squared equals energy psi x. I have to solve this equation. This is a differential equation, second order differential equation. Now if you look at this differential equation and you look at this term E, the potential energy is 0. Okay, so all of this energy is kinetic. Okay, so all of the energy of the electron is purely kinetic in this region because the potential energy is 0. So can you simplify this expression for me a little bit? Yes, this term can be written as 2m over h bar square. The energy is p square over 2m. This is p square over h bar square. But what is p square over h bar square? It's k squared. Okay? 4 pi square over lambda square. This is k squared, the wave number. So I can simplify this expression a little bit. I can write d square psi x dx squared plus k squared psi x equals 0. Now please solve this for me. ऊपर देखो k स्क्वायर.
सर वो पार्शियल डेरिवेटिव ऑफ m होगा h bar स्क्वायर प्लस e के साथ.
क्या
सर वो जो e के साथ आपने पार्शियल डेरिवेटिव ऑफ m ओवर h bar स्क्वायर.
पार्शियल डेरिवेटिव नहीं 2 है.
आई थिंक
2m. ठीक है. रेसिटेशन 1.1 इसी दिन का मैं इंतजार कर रहा था कि वो इस्तेमाल हो, वो जो आपने सीखा है. Has anyone been able to solve this equation? Mustafa is taking the lead everywhere.
E power iota k. E power iota k. Within the potential you have written 2m square.
Right.
तो m2m लिखा है. Which 2m square?
2m है
2m square I mean that.
वो गलत मैं ठीक कर देता हूँ. इसको एक्सपोनेंट की टर्म में लिखो. Just that. It's a second order differential equation. There must be two constants. किधर है solution?
It is by k cube over 3.
You see, it's a second order differential equation. There must be two constants. Which one? K is not a constant. K is 2me over h bar square. Two arbitrary constants, integration constants. So, I'm not going into the details of solving this. This is your responsibility. I take this equation, I find the characteristic equation, let's call it r squared plus k squared equals 0, which means r squared is minus k squared, which means r is plus iota k and minus iota k. Therefore, the solution is psi x equals a constant a ei kx plus a constant b e minus I kx. So inside the region 2, the wave function is given by this expression. Here a and b are two arbitrary constants. Please be quiet. Please be attentive. A and b are two arbitrary constants, and we have to find out what those constants are. It's a second order differential equation, hence we have two arbitrary constants and we want to find those out. अली जरा इसको कहना जरा इसकी आवाज तेज कर दे. All right. Now, how do we find out these constants? We know that if I draw the potential well, in this region the wave function is 0. In this region the wave function is 0. Now I am plotting the wave function with the blue color. So what is the wave function at x equals 0? What's the value of the wave function at x equals 0? 0. And what's the wave function at x equals L? It's 0. Now the wave function is continuous, which means it cannot suddenly change its value. So inside the potential well, the wave function appears to be this. Outside the potential well, the wave function is 0. So at the wall, the wave function must be 0. That wave function must also be 0 because the wave function has to be continuous. The wave function cannot instantaneously change its value. So that wave function must also be 0 at this boundary. What is the value of x here? It's 0. So the wave function psi in region 2 at x equals 0 equals a e raised to power iota 0 is 1 plus b. What is this equal to? 0. Because the wave function has to be 0 here. Okay? Now if a plus b equals 0, what's b? b equals minus a. So the original wave function in region 2 as a function of x becomes a e I kx minus a e I kx, and this becomes a e I kx minus e minus I kx. Okay, what is this? It's not cosine, it's sine. It's a minus sign here. It's 2 iota sine kx. 2 iota a sine kx. This is your wave function inside the well. We can also find out the value of a. Okay, that's not a problem, but okay, we'll do that in a minute. But let's look at what happens at this boundary. At this boundary, what's the value of the wave function? 0. So if you take this wave function and put x equals L, so this wave function 2 at x equals L is 2 iota a sine of kl. What is this equal to? This has to be equal to 0. 2 is not equal to 0, iota is not equal to 0, a cannot be equal to 0, because then the electron will not exist at all. The wave function is going to be 0 everywhere. So we have no electron if a equals 0. So the only possibility is that sine kl equals 0. Okay? Now when is sine kl equal to 0? When kl equals 0, that's it. 0, pi, 2 pi, 3 pi, 4 pi, and so on. So whenever kl equals n pi or k equals n pi over L, do we have a solution? K must equal n pi over L if the wave function has to be continuous. So the values of k that are possible are pi over L, 2 pi over L, 3 pi over L, and so on. This means that k is quantized. K cannot take arbitrary values. And what does it tell us about the energy? The energy is given by h bar squared k squared over 2m, p square over 2m, right? This expression that I wrote, E equals p square over 2m, p equals h bar squared k squared. So the energy is h bar squared k squared over 2m, but k itself is quantized. K cannot take any value, it can take only discrete values. So the energy as a result becomes quantized. So I can put h squared over 2m, k squared is n squared, pi squared, L squared. So this is an astounding result. A wave function exists, the electron is in a potential well, you apply the boundary conditions, you cannot get arbitrary values of k. K has to become quantized, and that quantization is because you're confining the electron. The rule of modern physics is that confinement leads to quantization. Whenever you restrict the particle to exist in a certain region and it do not allow it to go out of that region, which means you're binding the particle, then it results in quantization of the energy. The energy is now quantized. Okay? So if inside the well, if I make a plot of the energies, this is my potential well. Okay, let me draw a fresh diagram. This axis, this vertical axis represents energy. Now what are the values of possible values of n? N can be 1, 2, 3, 4 and so on. Okay? These are the possible values of n. Okay? Now when n equals 1, what is the energy? The energy is h bar squared pi square over 2ml squared. Okay, when n equals 1. So when the electron is in the well, it can have different values of n. N can be 1, 2, 3, 4 and so on. Which means that k can be pi over L, 2 over L, 3 over L and so on. K, 2 pi over L, 3 pi over L and so on. The energy can be n squared multiplied by this factor, h bar squared pi squared over 2ml squared. N squared, n goes from 1 to 4 to 2, so you have 4h bar squared pi squared 2ml squared, then you have 9h bar squared pi squared 2ml squared and so on. So what you have is a lowest energy state when n equals 1. Remember, n cannot be equal to 0, because if n were 0, then k would be 0 all the times, and k would be 0 all the time means that this wave function will be 0 all the times and the electron will not exist. So the minimum value of n is 1. So when you have this minimum value of n, the energy is given by h bar squared over 2ml squared. This is n equals 1 state of the electron. The electron can be in this state, and its energy will then be equal to, let's call this E naught. The energy will be equal to E naught. Now this energy is not equal to 0. Okay, so if the electron is in the ground state, in its lowest energy state, it cannot have 0 energy. It does not have 0 energy. There is always some residual energy that the electron can have. That is called the 0 point energy, and I will elaborate this concept further, but for the time being, n equals 1 is the ground state. What is the next state? The first excited state, when the electron can have the next highest energy. For that particular state, n equals 2, and the energy of the electron is going to be 4 E naught. The electron cannot have any energy in between E naught and 4 E naught. So the energy has become quantized. So confining the electron has resulted in the quantization of energy. Only discrete units of energy are possible. The electron cannot have any energy in between E0 and 4E0. Then what's the next state the electron can be in? If it has more energy, it can only have 9 times E0. N equals 3, 9 times E0. Then N equals 4, 16 times E0. Okay? So what we observe here is that the energy is quantized. Now what about the wave function? The wave function is inside the well is 2 iota A sine of kx. Now what is k? K is n pi x over L, right? So this is your wave function. So I would also like to plot what the wave functions look like. If n equals 1, that is the electron is in the ground state, what does your wave function look like? It's sine pi x over L. Sine pi x over L means a wave function that looks like this. This is the wave function. Sine 2 pi x over L means a wave function like this. Sine 3 pi x over L means a wave function like this. Sine 4 pi x over L means a wave function like this. So I will explain this in detail later. Can you please turn on the projector? I will explain this in detail later tomorrow as well, but just to surprise you, if the electron is in the ground state, first of all, it cannot have zero energy. It has some residual vacuum energy called the ground state energy, some 0 point energy. In quantum mechanics, nothing can be at rest, in other words. Everything is in constant, incessant motion. Second point is that the electron is avoiding the walls. This is a wave function, a picture of the electron at any one instant. It's a snapshot of the electron. The electron is everywhere inside the well. Now when you measure the position of the electron, you can detect the position to be anywhere. You can detect it to be here, 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 here. But with maximum probability, the electron will be found at the center of the well. It's going to avoid the wells, the walls. If the electron is in the first excited state, you will never find the electron to be in the exact center. You will never find the electron to be at the exact center of the potential well, and so on. I have a demonstration to show, so after that, so we don't miss out on the time. One thing I would like to demonstrate is in the form of a nice experiment. But if you look carefully here, this is E0, this is 4E0. If I change the length of the well, will this level go up or down? If I increase the length? Down. If I increase the length, the energy will go down. Okay? And if I make the length smaller, this energy level will go up. Okay? So changing the dimensions of the object, the size of the object, changes the energy spacings. Now suppose I have an object called a quantum dot. A quantum dot is a nanoparticle of dimensions roughly of the order 1 nanometers, 2 nanometers, 3 nanometers. And the energy levels inside the quantum dot for the electron, they are quantized. Okay? So now you have a simple diagram would mean, a very simple diagram would mean that this is a ground state, this is an excited state. Ground state, excited state. And then there are states above. Okay? If I reduce the dimensions of this quantum dot, if I make this quantum dot smaller, then the energy spacing between E0 and E1 is going to increase. Okay? So then I have a E0, E1, and energy levels above. So if an electron were to make a transition from E1 to E0, what will it do? It will emit a photon of a certain frequency. Now if I reduce the size of this quantum dot and then an electron is emitted by making a transition from the excited state to the ground state, a photon will be emitted. Which photon will have the higher frequency? This one, and the shorter wavelength. Okay? And then if I make the size of this quantum dot even smaller, these energy spacings are going to increase, and the photon that is emitted will have higher and higher frequencies. Which means that by restraining the electrons further and further, by confining the position of the electrons, the energy spacings go up. And if you somehow excite an electron that was initially in the ground state to one of the higher levels, and then it makes a downward transition gradually and then reaches here and then falls down, a photon will be transmitted, a photon will be ejected, and you look at the frequency of this photon. By looking at the frequency of the photon, you can tell what the size of the nanoparticle is. So just by changing the size of this quantum dot, you can get photons of different frequencies, of different colors. This process is called fluorescence, as you already know. So the color of the photon that is emitted is a signature of the size of the nanoparticle, the size of the quantum dot, and the energy spacings between the energy levels. So what we've done for you is that Murtaza and Rabia, they have prepared a demonstration, and the demonstration works as follows. Ali, is the light off? So we have prepared some solutions of quantum dots. These are semiconductor quantum dots made up of cadmium selenide quantum dots, and we made them of different sizes. Okay, 1 nanometer, 2 nanometers, 3 nanometers, 4 nanometers in our physics laboratory. And if you observe here, these solutions, they have different colors, just because the sizes of the nanoparticles inside these colloidal solutions is different. This is it a smallest, or this is red? This is a longer wavelength, smaller frequency. So these are bigger nanoparticles, and these are smaller nanoparticles. Have you done such an experiment in your chemistry laboratory? No. Okay. So here is diagram. Can I have एक और laser pointer होगा कोई इनके पास ये काम नहीं कर रहा. This is a diagram. I've also uploaded this presentation. You have energy levels above and below a band gap, and when an electron falls from a high energy level to a low energy level, a photon is emitted. Now if I decrease the size of these quantum dots, that is, I reduce L. If I reduce L, the energy spacing goes up. And if the energy spacing goes up, if a photon would fall down from a higher level to a lower level, it will emit a photon of higher energy, of higher frequency and of a shorter wavelength. Now, I've also uploaded the mechanism for synthesizing these quantum dots. How do we make these quantum dots? These are cadmium selenide quantum dots. It's a semiconducting material. You prepare two solutions, one with the selenium and one with the cadmium, and then you mix the two. And there is actually also a video that shows you how to prepare these quantum dots. So physics is talks very closely to chemistry. You cannot have physics without chemistry, and you cannot have chemistry without physics. So both of them go together. So there is actually a detailed video. It's about a 12 minutes video which actually shows you how to prepare these. It's an annotated video. It will actually show you how we prepared those solutions. It has all the steps in it. So if you would like to do it in your chemistry laboratory, you can do it. Here you can see something strange happening. There's a magnetic stirrer that is stirring the solution, and it's a magnetic hot plate. And then as you put in different solutions, the color keeps on changing because the size of the quantum dots keeps on changing. First you have smaller quantum dots, and then they gradually build up in size. So you pick out those quantum dots after regular intervals, and you get an array of quantum dots of different sizes. Okay. And then you closely monitor what the temperature of the synthesis is. Goes up to 200 degrees centigrade, and then you can see the change in color. First a solution becomes transparent, and then gradually it starts changing its color. So color tells you the size of the nanoparticle. The fluorescence wavelengths tell you the size of the nanoparticle. The only difference between what we've seen on the blackboard is that on the blackboard we've looked at a one-dimensional problem, just one length, but this is a three-dimensional object. But the general rule follows the same pattern. So these solutions are picked up from the solution and they are poured into test tubes. As you can see, the color of the solution is constantly changing because the size of the nanoparticles that are synthesized, that's constantly changing. So this was the video, and this is what we expect. So if you have different sizes of quantum dots of nanoparticles, all the way from 1 nanometers to 16 nanometers, the wavelength keeps on changing. Larger radii nanoparticles have longer wavelengths or smaller frequencies, smaller energy gaps, and there's an exact equation that can be modeled, that can model this behavior as well. And this is what we obtain practically. You have bigger sized nanoparticles. As you go to the bigger sized nanoparticles, the wavelength of the emission peak shifts towards the right. Now I'm going to show you a practical demonstration. For this practical demonstration, let me first show you what the setup looks like. Okay. नहीं टर्न ऑन लाइट सर, एक मिनट जला देंगे, पहले मैं इनको दिखा लूँ स्टूडेंट्स को. ये बल्ब ऑफ कर दो. So now what we have here is basically this is basically a light source. It's a laser. It's a blue laser. It shines light onto these test tubes. This is a series of test tubes of quantum dots of varying sizes. So here we have, first of all, we are focusing on the quantum dots with the largest size, and we expect that the light that these quantum dots will emit will be of the longer wavelength, smaller energies, smaller frequencies. And at the very end we have an optical fiber that picks up the emitted, the fluorescent emission, picks it up, takes it into an optical fiber. It's a long optical fiber. This optical fiber goes into this spectrometer. This spectrometer takes the spectrum of the light emitted, and these are rails which help us bring one sample after the other into the path of the laser beam. The original blue laser beam is exciting the electrons. It's a blue, so it's 400 nanometers. So it excites the electrons to some higher energy level, and these electrons then fall down gradually till they come to this level, and then a downward transition takes place. And when this downward transition takes place, photons of a particular frequency are emitted. So I would probably need your help, someone's help in actually. So I would like to wear goggles because this is a so I've turned on the laser light. Laser hai? Laser hai? Turn on the spectrometer. ठीक है इतना चलिए. लेजर काम नहीं कर रहा. Alright, so now what we observe here, I hope you can see what's happening from the so what's happening, I hope you can see what's happening. A particular wavelength is being emitted from the fluorescence emission, and now that fluorescence emission is at around, there's a peak, ध्यान से सुने, there's a peak at around 610 nanometers. And this green line shows you where the peak of the fluorescence emission is. Now we are focusing on the biggest size nanoparticles. So the wavelength is longest. Now we move this assembly so that we gradually move on to the next smaller nanoparticle. Lights on कर लें इसमें. All right, now you can see a hump. You're at the next test tube. You're at the next test tube. This is the emission. This is the spectrum from the original laser. And now you observe that the peak has shifted slightly towards the left. towards the shorter wavelengths. Now if you can gradually move to the next one, please. And once again the maximum of the peak has shifted towards the left. So you were observing those extra peaks because you had the lights on. Is this water? Once again, you have a shift towards the left. And this, the leftmost peak, the sharp peak, this peak corresponds to the laser. Now one question I would like to ask you, before we do the last step. Why is the left peak? Why is this peak sharper than this peak? Please raise your hands and tell me why is this peak from the laser more precise in wavelength, in frequency and in energy as compared to the emission from the quantum dots? Anyone from the back, please? आप बताइए. No, that's not the reason. The quantum dot's direction of emission has nothing to do with the spread of these frequencies. आप बताइए. So one reason is that in the quantum dot there is not only one transition that is taking place from the upper level. There are many transitions that are taking place. So photons of different frequencies are being emitted. But even if photons of one frequency were being emitted, this line would be sharper than this line. Reason? B. One, the samples, the colloidal solution do not have one radius of nanoparticles. There is a dispersion in the sizes of the nanoparticles, which means we do not have a monodispersed solution. There is a range of sizes. It's averaged at some radius, but there is a range of sizes. That's a good point. So you have photons of different colors being emitted. Still, is there yet another reason why this peak is so sharp? Stimulated emission. आप बताइए. exactly the excited state of the energy levels inside this blue laser, gallium nitride laser. The excited state has a very long lifetime. It's a metastable state. Therefore, the delta omega, the precision in energy is very sharp. The range of frequencies emitted is very sharp. So it's because of the uncertainty principle that this peak is much sharper. And the last sample we would like to show you is the following. Now you do not observe any emission because the last test tube contains only water. There is no fluorescence emission from the last test tube, there is only water. So this is a control signal. So all the fluorescence is actually coming from the cadmium selenide quantum dots that we prepared. And what I tried to show you today is that the size has indeed an important bearing on what we observe from quantum objects. So see you tomorrow, inshallah. And tomorrow there's going to be a quiz as well.